Let's continue exercise 3.3 on the simulation using RCSTR. So remember, we are having an isomerization of cis-2-butene to trans-2-butene, and we are asked to determine the residence time that allow us to achieve the conversion of 90%. So based on our base case simulation, with the residence time of 5 minutes, we get only about 53.5%. So with this, we have to increase either the residence time manually, or you can use the design spec function to vary the residence time in order to achieve the targeted conversion. Of course, we would like to know how to use design spec so that we can solve the problem easily and quickly. So what you need to do is you just use the backup file that you have created for exercise 3.3 just now. What you need to do is you have to go to this flow sheeting option, okay, under design spec, click new. You'll be given a name of the S1 to indicate that this is the design spec first analysis. Proceed further, just click next to proceed further. You need to complete the information in these three tabs. We have define, spec, and also vary. So let's define the parameters that we are going to use when we want to set the specification later on for conversion. So obviously for conversion, in order to write the equation for conversion, you need the molar flow rate of the reactant in the inlet as well as the outlet. Okay, so you have to first define F outlet, the molar flow rate of the cis-butene in the outlet. So just put the name. I think this one you can actually create on your own, the name. Click new, put the name, and then you have to define accordingly. So this is a stream variables. The type is molar flow, and this is in our outlet. S2 is my outlet stream, and the component that we want is cis-butene, and the unit is kilomole per hour. So on top of the molar flow rate of the cis-butene in the outlet, we also need the molar flow rate of the cis-butene in the inlet. So create another one, F in CISB, and then you define accordingly. So next is for us to include our spec for the targeted parameter. Here we are targeting the conversion. So the equation for conversion you have to put under the spec. So F in minus F out for the cis-butene over the F in for the cis-2-butene. So this is the equation for conversion. We are targeting 0.9 with the tolerance of 0.0001. So this one, it depends on the accuracy of the results that we want. So we only allow, this is quite stringent, meaning we only allow the conversion of 0.9 plus minus 0.001. So this is the allowance that we allow for the simulation to converge. So with the spec done, then we move forward. We have the vary tab for us to include the varying parameters. So this is more or less the same with the one in sensitivity analysis, if you still remember. So another function that you learn is sensitivity analysis. So now in design spec, again we have to put in the varying parameter. So we would like to vary the residence time, and we know that residence time is the block variable. Which block is it? It's R101 because we have only one block in the flow sheet. So the unit that we should choose is minute. We would like to vary from 5 to 40 minutes with the step size of 0.1, meaning the simulation will be done on 5.1, 5.2. So this is the meaning of step size. Right? And with this done, I think we have all the information in for the design spec. Just run the simulation and check the result. When we have it done and the results are available, under DS1 we have the results. We check the final value. Here it is stated that when the conversion is 90%, the F out, the molar flow rate of the cis-butene in the outlet should be 0.1, correct? And the residence time required is about 0.65 hour. If you change it to minute, it's about 39.13 minute. So with this answer, we actually verified the manual calculation, right? Just now, using the manual calculation, or using the analytical solution, we also get the same answer. Right? So other than the result just now, you can also check the results and also string results under the block section. So this is a block section. So we have the results here. So residence time, you see, is 39.13, and the volume required is about 61 liter. This is the reactor volume required. You can, if you have residence time, then you can have the volume. If you specify the volume, then the residence time also can be calculated accordingly after the simulation. So molar flow rate, you can check under the string results. Of course, if you have the design spec, once you perform the design spec, the results under the block will be changed accordingly in order to achieve the 90% conversion. That means the old result will be substituted using the findings from the design spec. So I think that's it for exercise 3.3. So we have another exercise here, exercise 3.4. The reaction is the same. We have isomerization of cis-2-butene to trans-2-butene, but this time we are going to determine the residence time to achieve the 90% conversion in a plug-flow reactor. The details of it you can refer to our X006 PDF file which is given to you. And based on the manual calculation, we found that the residence time required to achieve the conversion of 90% is about 10 minutes, and you need to verify this manual calculation answer using the X1 Plus simulation results. Let's analyze the problem before you solve it or before you take it home and solve it. So we have a reactor model here. Of course, it's RPFR, number of feet, the feet specification is the same with the CSTR. It's just reactor specification here, other than the temperature, pressure, and also the phase, the valid phase of the reaction. The diameter of the reactor is 2 inch, and the length you have to first specify as 1 meter, because later on you have to try to vary the length of the reactor to determine the desired conversion, meaning you have to identify the length of the reactor which allow you to get the conversion of 90%. So the rate information here is the same as the CSTR just now. So with this, I would like to make a conclusion here before you can take exercise 3.4 back to home and solve it. Kinetic data is required if kinetic-based reactor model is used. You have to bear this in mind. If in the question, kinetic equation or kinetic data is not given, then just forget about the kinetic-based model. And design spec function should be used to identify the operating condition used to achieve the targeted conversion. It can be conversion, it can be selectivity, or it can be you can specify under the design spec function for all this equation. Okay, now it's your task to solve exercise 3.4 using RPFR before our next class. Thank you very much.